One big application of this motional EMF for this induced current is the use of a generator. This is how all generators generate electricity, in that we are changing the magnetic flux. So remember, flux is defined as BA times the cosine of theta. So B and A are constant for this loop. We are changing theta by rotating it. So this converts mechanical energy to electrical energy. You need to turn it and electricity comes out. And so instead of moving it in a linear direction like we just talked about, it's spinning. So this is a much more sustainable, that it's not going anywhere, it's just sitting there and spin. So any generator is basically a motor running in reverse, and it consists of a magnetic field, either an electromagnet or a permanent magnet, and a loop of wire that can spin. And so there are a variety of sources that we can use to make the loop turn, and that includes falling water, heat from coal that produces steam. There's lots of ways that we can put energy in to be able to turn this generator to make the electricity. So the basic operation is pretty much like a motor. These things are indistinguishable. They're the same device often. There are some slight design changes, but they're basically the same device. So as the loop rotates, the magnetic field flux changes with time. This creates an EMF and thus a current. The ends of the loop are connected to make AC power. The ends of the loop are connected to these slip rings with brushes. And so basically, as the current flips over in direction because of the flip in orientation of the armature, then the direction of the current will also flip. What you see down here is that the current is constantly changing directions. So these connections to the external world are made with brushes. They're little, basically, they're just like hair brushes of wires touching the brushes to the armatures. So how do these generators work? As EMF is produced by the rotating loop can be found by, we have two ends of the loop, so 2 BLV. And so if we condense that formula, then we end up with NBA as the maximum. So this is E max when the armature is in the correct orientation. And how real generators work is they actually have 3 pickups and output what we call 3-phase power. So the 3 phases are all alternating in sync with each other because of the way the generators are produced. So anyway, the NBA is the maximum when the loop is parallel to the field, and at a minimum when the loop is perpendicular to the field. So we're going to take another look at that. So perpendicular to the field, there's no generation of electricity because there's no magnetic field. The flux is basically gone to zero. Then as the magnetic field is at a maximum, so here I is at a max, then the EMF produced is also at a max as we rotate through the magnetic field. So the magnetic field is stationary, but the loop is rotating. So the magnetic force on the wire changes in direction as we go through. And you see little green lines appearing in this little animation as the force on the magnetic field switches the direction. So the EMF is generated on wires B, C, and AD. So on this top one and the bottom one, and the EMF produced in each of the wires is equal to BLV, the same formula that we've seen before. So DC generators can also be used, and these uses what we call a split ring commutator, just like the DC motor does, except what we get out of it is we still have a rise and fall because we have a maximum and a minimum when the loop is either parallel or perpendicular to the magnetic field. But what happens is this just kind of gets smoothed out by most of the electronics. And we have other gizmos that we can use to smooth out that the voltage, so it's basically constant. But the idea is that for direct current generators, the current's always going in the same direction. The potential difference is always in the same direction. So DC generators always output the same direction, is what we just said. And it's a little bit pulsing, but again, we have ways to kind of flatten that out. Okay, so now we're going to do some math. So here we have a generator. It doesn't really matter in this case if it's AC or DC. but we want to figure out what the speed is. Well, what are we given here? So we know that we got 2 centimeter by 6 centimeter. That looks like it's going to help us give some sort of area. This is our N. We have amount of Teslas, that's B, and we have the EMF generated. So we know that E as a function of time is equal to omega NBA times the sine of omega T. And we know that this is the maximum, the amplitude. So amplitude is code word for a max. So our EMF max is at 17. So if we're looking at a maximum, then we're just looking at the sign of 1. And so E max is equal to W NBA. So there I can solve for my omega is equal to E max over NBA. And that's equal to 17 volts divided by 80 times 0.45 times my area is 0.02 by 0.06, and that gives us a total of 390 radians per second. So that's how fast it's spinning to be able to create that much power. So if I wanted to look at this formula, if I can increase any of the formula, the N or the B or the A, I don't have to spin it nearly as fast. Now it's your turn. So slightly different variables. Here we're given the omega, but remember to convert that to radians per second. We're given B, that looks like an N, and we're given area. So see if you can figure out what the maximum EMF generated in this case is. Okay, well hopefully you figured it out. So E is equal to E max is equal to W MBA again. So 16 cycles per second, and we need to convert that to radians per second. Remember there's 2 pi radians per cycle. And then we have N is 100, B is 1.3 Teslas, A is 50 centimeters squared, but remember we got to convert that to meters squared, so 1 over 100 squared, centimeters squared per meter squared, should give us an answer of 245 volts. So there we go.